All right, 6.3, proving identities. Proving trigonomic identities is what we're going to focus on today. To prove an identity is true for all permissible values, we must express each side of the equation as equivalent. On both sides of the equation must be algebraically manipulated without affecting the other side so that they match. So that is the goal. So a few tips for proving identities. I always start by simplifying the more complex side. So if you look from left side to the right, pick the more complex one. If they're about the same, then it doesn't matter where you're going to start. Use known identities to make substitutions. So we have our sum and difference identities. We have our quotient identities, Pythagoras identities, and reciprocal identities. So we're going to use those for substitutions. We're going to try to rewrite expressions in sine or cosine only. So that's kind of our goal, is you generally want to work in sine and cosine. Sometimes you'll leave it in a tangent expression. If we see some kind of quadratic, you might want to consider the Pythagoras identity first. Sometimes you might have to multiply it by the conjugate in order to manipulate it. Sometimes you might have to look to factor to simplify expressions. And then you're never going to move expressions from one side to the other of the equation. You are not solving an equation, you are simplifying expressions. So you're simplifying the expression on one side versus the other side. Okay? So the first example, 1 minus sine squared x equals sine of x equals times cos of x times cotangent of x. So we're first going to prove this identity numerically. So I'm going to choose a numerical value that I'm going to prove the identity for. So I'm going to choose equal to pi over 2. So what that means is I want to substitute pi over 2 for x, and then we are going to simplify each of these expressions. So on my unit circle, sine of pi over 2 equates to 1. But here it needs to be squared because it's sine squared. Sine of pi over 2 all squared. Sine of pi over 2 is also 1. Cos of pi over 2 is 0. Cotangent of pi over 2 is also, it's off in my unit circle. If I simplify the left side, 1 minus 1 gives me 0. 1 times 0 is 0. So, and it's okay to get a value of 0 in your proof. It's a number like anything else, so 0 equates to 0. I've proven the identity numerically. And we want to state the non-permissible values. So our non-permissible values are going to, we don't have to worry about this. We don't have to worry about sine. We don't have to worry about cos, but we do have to worry about cotangent. We know cotangent of x is the same as cos over x over. So what we have to consider is we have to consider the denominator of this fraction. So sine of x cannot equal 0. When does that occur on my unit circle? Well, when does sine of x equal 0 would be at 0, pi, 2 pi, and so on. So my non-permissible values would be x cannot equal n pi n, where n belongs to the integers. That would be my non-permissible values. All right, now we actually want to prove this identity using algebraic expressions. So I'm going to, again, write out this identity. I'm going to look at the identity and recognize, well, to me, the right side looks a little bit more complex than the left. So I'm going to start by this. I can't really change sine of x to anything. Can't change, but I can replace cotangent of x with a cos of x over sine of x. And so what happens here is, because this is all multiplication, right? This sine of x is going to cancel with this. So then what I'm left with is a 1 minus sine squared x equals cos squared x. I'm going to go to my formula sheet and either try to replace cos of x with something, or 1 minus sine of x with something? Well, I do know on my formula sheet, or my Pythagoras identity, right, if we are to think about our Pythagoras identity, here it is, cos squared x plus sine squared, our formula sheet. But remember, we can manipulate this identity to solve for either one of these values. So if I solve for cos squared theta by moving sine squared theta to the other side, cos squared theta is equivalent to a 1 minus sine squared theta. So that's what I'm going to replace here. A 1 minus sine squared x is actually equivalent to cos squared x. And so now that I've proven that my left side and my right side are actually equivalent, I am done. So this has to be your end result. The left side has to look at the as the right hand side. Okay? And you have to show every step so that it is clear that you understand this expression equals this expression, and so on. Okay? All right, so we're going to spend the next 5 examples proving trig identities. Okay? So next one, I'm given tangent of x is equal to a sine of 2x plus 1 over 1 plus cos of 2x. Sometimes there's lots of different in order to prove an identity, so as long as your proof works out in the end and all of your algebra is correct, then you'll get full marks. I might see things different than you might see things. The other way you can think of identities is like solving a puzzle. Sometimes try something, get 2 or 3 steps into the question, and it's not taking you anywhere, so then you might have to go back to the start and start over, try a different piece, right? My rule of thumb is normally if step by step your expressions are getting more complex, then that's kind of a red flag to say, okay, I need to go back and change something, because step by step, especially by the 3rd step, things should start to be simplifying for you and getting more simple as opposed to more complex. Okay. All right, so looking at expression, I'm going to look at the right side and I'm going to say, well, the right side definitely looks more complex than the left, so I'm going to leave that tangent of x for the time being, but every step it needs to be included in my proof. Okay, or often I will use a quotation mark for my left side, and then at the very end I'll rewrite it. Okay, so sine of 2x. This can be replaced with my double angle identity. So I'm going to change this to 2 sine of x cos of x. Same with cos of 2x here. Now again, I'm going to try to look at this one value and say, right now technically I have 2 fractions here. Like I would separate this over 1, right? If I were to separate this, I want to eventually write this as all one big fraction. So somehow this denominator has to become a single trig expression. And so somehow I want to get rid of this 1. Well, to get rid of that 1, I'd have to subtract 1. So when I look at these double angle identities, again, in order for that positive 1 to cancel, I would need a negative 1. So this kind of tells me out of these 3 identities, I'm going to replace cos of 2x with this one so that my 1's cancel. So I'm going to go 1 plus, I'm going to replace cos of 2x with a 2 cos squared x. So then my next step, I'll just put quotations here for tangent of x. Right, and it's important to show that every step, so whoever is marking your paper understands every step that you're going. If you skip 1 or 2 steps, they're going to say, well, do they really understand how to go from one step to the next? So it's really important that you do not skip steps. So it's pretty obvious here that my 1's are going to cancel, so this would be my next step. From here, tangent of x is on my left. So now I would show my 2's cancel. I would show this cos is going to cancel with one of those, and I'm left with sine of x over cos of x. So now I recognize that this is definitely equivalent to tangent of x, but if you left this as your final step, you would not get full marks. You have to show your final step where equivalent expressions in the end. So you could change your tangent to sine over cos, or I'm going to change my over cos of x to tangent of x. So this would be my final step, right? That my left side equivalent to my right hand side expression. All right, moving on. Question B. I'm given 1 minus cos of x over sine is equivalent to sine over 1 plus cos of x. So when I look at these expressions, well, I can't really change sine into, I can't really change cos into anything. There's no double angle occurring anywhere. I can't use Pythagoras identity because it's not a cos squared x. So I'm kind of like, at this point, I don't know what to do. So this is where we consider multiplying by the conjugate. After a right-hand side, it honestly wouldn't matter. So if I took the right-hand side and I multiplied by the conjugate of 1 plus cos of x, the conjugate of that would be a 1 minus cos of x. So that's what I'm going to do. I'm going to multiply the right side. So I'm just going to work with the right side. I'm going to leave the left side alone. And I'm going to multiply numerator and denominator by 1 minus cos of x. So my left side is going to stay the same. I'm just going to leave that in quotation marks. Here I would have to multiply the sine of x through my set of brackets. Or not even. Eventually I want this to maybe stay a 1 minus cos of x. So I'm going to do it in factored form for now, just to see what happens. In my denominator, I'm going to actually want to FOIL this out, so expand it. So first times first, 1. Outside times outside is a negative cos of x. And then I get a plus cos of x, so those are actually going to cancel each other. And then I get a cos of x times a negative cos of x is a minus cos squared x. All right, so that would be my... Now I'm going to look and start to recognize that a 1 minus cos squared x, this is my Pythagoras identity. Pythagoras identity, right? If I were to solve for either of these two values, if I moved cos squared x to their side, that's going to be equivalent to a sine squared x. These two expressions are not on your formula. Recognize how you can manipulate this Pythagoras identity. So I can replace a 1 minus cos squared x with a sine squared x. So again, I'm not really doing anything with the left side of my identity yet. So then look what's going to happen. So it's a good thing I didn't run this sine of x through my brackets, because this sine of x is actually going to cancel with this in my denominator. So look what we are left with. So now I'm going to write my left-hand side 1 minus cos of x over sine of x. That didn't change. But on the right-hand side, I'm left with the exact same expression. So once you get to this point where your left expression is the same as your right, you're done. Regardless of how you wouldn't have to simplify it any further, you'd be done. Okay. Question C. We have a 1 minus tangent of x equals cos squared x minus sine squared x all over a cos squared x plus sine of x cos of x. So again, lots of things happening here. I really don't see a sum and difference identity. I do not see Pythagoras, because Pythagoras is a cos squared. I don't see any double angle identities. So again, I feel like I'm stuck a little bit. So the next possible tip to proving identities is to look to factor. So I'm going to factor this as a difference of squares. This is like saying we have an a squared minus a b squared here. So how do we factor that? So again, I'm going to leave the left side alone. So it's going to be 1 minus tangent of x. I get a cos of x plus sine of x times cos of x minus sine of x. Right? It's like factoring an a squared minus b squared would be a plus b, and an a, kind of the same idea. And then in the denominator, I'm also going to factor this, but I'm going to factor out a GCF. So a greatest common factor. So I'm going to factor out a cos of x here, and I'd be left with cos of x plus sine of x. All right, so once I've done that, look what happens. This whole expressions are going to cancel with each other. All right, so now what am I left with? I'm left with cos of x minus sine of x all over cos of x. Okay, I cannot cancel these cos of x's because we have a minus sign in between these values. We can only cancel across multiplication or division. So my next step, again, I don't see any double identities here, sum and difference identities, so we're kind of at a standstill again. But what I am going to look at is over here, I technically have two fractions occurring. Right? I have this fraction minus this fraction. On the right side, this is all clumped together as one fraction. So what I want to do is I'm going to separate this, right? I want these expressions to look the same. So I'm going to separate into two fractions. So again, I'm not going to do anything with my left side. I'm just going to put quotations there for now. So how do you separate this into two separate fractions? Each of these numerators would be over the same denominator. So this would be cos of x over cos of x minus sine of x over cos of x. So now it's kind of looking good here now. So now I'm going to take a 1 minus tangent of x is the left side. Cos of x divided by cos of x, well, anything divided by itself would be 1 minus sine over cos is 10. And we are done. So lots of different things you need to look for sometimes, right? In question B here, we looked to maybe multiply by the conjugate. Here I looked to factor. I use my factoring skills. I use fraction skills to separate fractions. So it's really important that you start to, if you don't do enough practice with your identities, then you're not really ever going to know what to do. So it's important that you practice lots of different questions so that you start to recognize what you would use when. Okay? All right, and then our last couple examples here. Question D, we're given a sine squared x over a 1 minus sine squared x plus 1 sine squared x over 1 plus sine of x is equal to a 2 tan squared x. So again, I am going to look at this expression and say, well, my left side is definitely more complex. So how could I simplify this? So when I look at this, I say, well, I probably could change my sine squared x using my Pythagoras identity to a 1 minus cos squared x, but is that going to get me anywhere? Okay, and so the other thing you're going to look at is similar to the last question, is the right side of my question is technically written as a single fraction. The left side of my equation is technically written as two fractions. So I somehow need to write or get this to be one fraction, right? I need to add these fractions. So in order to add these fractions, I need to find an E, a lowest common denominator. So we're using fraction skills here again. So in order to get a lowest common denominator, our lowest common denominator would simply be each of the denominators. This is like a 3 and this is like a 4. I'd have to multiply the two together to get a common denominator. So I multiply the first fraction by 1 plus sine of x. Multiply my second fraction by a 1 minus sine of x. And then that's all going to be over the same denominator of 1 minus sine of x times 1 plus sine of x. And then we have this expression on the right hand side. All right, so from here, I know lots of us would want to run this through our set of brackets, which kind of makes sense, but instead of doing that, I somehow want to like cancel things. So I am going to, instead of expanding, factor. So I'm going to factor out a common factor of a sine squared x here. And what I'm left in my square set of brackets would be a 1 plus sine of x plus a 1 minus sine of x. And then in the denominator, I'm going to expand this out in my denominator. So FOIL, first times first, is outside is plus sine of x, inside is negative sine of x, so those end up canceling. And then last times last, I get a negative sine squared x. And then this is 2 tan squared x. All right, so look what's happening here. So these are going to cancel inside my brackets. Those sine of x's end up going. 1 plus 1, I'm just left with a 2. So I'm technically left with 2 sine squared x in my numerator. In my denominator, a 1 minus sine squared x, this is our Pythagoras identity again, is equivalent to a cos squared x. Well, look what happens. A sine squared x over cos squared x is equivalent to tangent squared x. And we are done. So again, in this case, we look to actually add the fractions using a lowest common denominator. Okay, and then the last question, sine 4th x minus cos to the 4th of x is equal to 2 sine squared x minus 1. So to me, the left side looks more complex to the other, so I'm going to work with the left-hand side. Again, I recognize this as a squares, so kind of tricky. This, as a difference of squares, would be sine squared x plus cos squared x times sine squared x minus cos squared x. And then on the right side, we're left with the same expression. I'm not going to touch that yet. Well, look, sine squared x plus cos squared x, this is my Pythagoras identity. So this just equates to 1. So this is technically a 1 times sine squared x minus cos squared x. If I look at the right side of my equation, this is only in terms of sine, so I want to somehow change cos squared x so that it's just in terms of sine. Well, this is my Pythagoras identity as well. So I'm going to take a sine squared x minus, and then in brackets, I'm going to change this to a 1 minus sine squared x. This is still the same. I'm not going to touch that. I'm going to run my negative through my brackets. Still the same. And so look what I end up with. I have 2 sine squared x's minus 1, and that is going to equal what I have at the very top. So again, I did not manipulate the right side at all. I only manipulated the left side. And then there's my identity. All right, so that's it for proving identities. Again, it's really, really important